Hello, my little scientists. Welcome back for another lesson. So in this lesson, we will talk about stoichiometry. Now, this concept is a pivotal one in chemistry. It is very important. Some people find it a little bit more difficult to grasp, so hopefully I'll be able to make it clear and concise. If you have to listen to the video or watch a video more than once, that might help you. Now, for the present lesson, you are going to need a periodic table, a calculator, a piece of paper, because I would strongly encourage you to solve the problems along with me. So you might want to pause the video as well from time to time to try and do the problem by yourself before or after I solve it, depending on how comfortable you are with the concept. Okay, so let's take a look at the first slide. First, before I talk about chemistry, I want to talk to you about baking. You'll see there's a parallel to be made here. So you've learned how to balance equations. We know that balancing equations involves ratios. So we know that in real life, when chemical reactions occur, they occur in certain ratios. In other words, the substances that are reacting and the substances that are produced always react or appear in specific ratios. The same way, if I look at this recipe, this is just part of a recipe, but if I look at this recipe, I know that I'm going to need to make this zucchini bread, or you can make muffins, whatever. You're going to need a certain amount of flour, a certain amount of sugar, baking powder, and so on and so forth. So you have specific amounts. Now, if I wanted to double the recipe, I would have to double all my ingredients. I can't just say I'm going to double the flour but not the rest. The outcome will not be the same. It's the same thing in nature. The more particles participate in the reaction, well, the more products will be produced, but always in specific ratios. The same way I have specific ratios over here. Okay, so I just wanted to make the analogy because this might speak to you a little bit more. It's more of a visual, so it might help you understand the following concept better. So moving on to the chemistry part. So I have a reaction. Now, the coefficients in front, we know that they mean, for example, here that I have 2 molecules of H2. But in reality, what it also means is that 2 moles of H2 molecules are reacting with 1 mole of O2, and that produces 2 moles of H2O. Okay, so I have a ratio of 2 for 1 for 2. Now, I could translate this into a mass because we know that our scales don't measure moles, but they measure masses. But we know that there is a link to be made between moles and mass, right? Because we know that in 1 mole there is 6.023 times 10 to the 23 particles, could be atoms or molecules depending on what we're looking at, and those particles have a specific mass. So I could convert these 2 moles of dihydrogen into their corresponding mass. So as an example, I would have 2 times, because there's a 2 in front as a coefficient, 2 times the mass found in the periodic table for hydrogen times 2 atoms of hydrogen, right? Because there's a 2 here. So it's 2H2 times 2. So that's the mass of H2. There's 2 atoms of H2, but there's 2 moles of that molecule. So in total, that gives me 4.04 grams. So that's why I was telling you it would be a good idea to have a periodic table next to you so you can follow along. This is where I'm getting these numbers. I'm getting them from the periodic table, obviously. Now, if I do the same exercise for 1 mole of dioxygen, it would give me 32 grams. So it's a similar calculation. I did not give you the details. I'm assuming you know by now how to do this. So 32 grams for 1 mole of O2 gas. Water, H2O. H2O times 2 moles gives me 36.04 grams. So 2 times 18 essentially. When you use the masses in the periodic table, make sure to keep at least a couple of decimals when you calculate the masses, the molar masses. That will be useful when you do significant figures in your calculations when you solve a problem. You'll see a little later in this lesson why it's important to keep a few decimals. Okay, so if we analyze this whole situation over here, what is constant and what is not? So is the number of moles constant between reactants and products? I have 2 moles, 1 moles for a total of 3 moles of substance. And when it gets rearranged, I only get 2 moles of H2O. So the number of moles on both sides, comparing reactants to products, is not constant. So I'm not going to put a check mark over here. Is the number of molecules constant? Well, I have 2 types of substances here and only 1 over here. So that doesn't add up. So the number of molecules is not constant. Is the number of atoms constant? Well, if this equation is balanced, and it is, then the number of atoms is constant. I have 2 oxygens on this side. I have 2 times 1, 2 oxygens on this side. I have 2 times 2, which is 4 hydrogens on this side. And here I have 2 times 2, 4 hydrogens. So here I can say, yes, the number of atoms is constant. So I could put a check mark over here. This will always be constant. Are the masses constant? Well, is the law of conservation of matter followed? 4.04 plus 32, because these are my reactants, right? If we look at the equation, these are my reactants. So 4.04 plus 32 gives me 36.04. And on the product side, I have 36.04. So yes, the masses are constant. So in a reaction, what is constant? The number of atoms and their corresponding masses when we compare the reactants to the products. But the number of molecules is not constant. We don't have the same number of molecules on both sides, and we don't have the same number of moles on both sides. And that's because sometimes we're going to start with many different substances, and when the atoms get rearranged, we only get one substance, but a lot more of it, or the molecules are bigger. Okay, so as we have here, we have 2 types of molecules, but at the end, we only get 1 type of molecule, but the molecule is a little bit bigger than these individual ones. Okay, so it doesn't always add up in terms of moles or molecules, but it does in terms of atoms and their corresponding masses. So keep that in mind. Now, just like my recipe before, let's say I wanted to double my recipe, I have to double all the components, all the ingredients. Now, what if I wanted to double this reaction? What would the numbers look like? Well, you can see it's very tedious to do the following, to say, okay, I have H2. What is the corresponding mass, molar mass, and therefore mass of substance that's reacting for H2? What's the mass for O2? What's the mass for H2O? It can be very long to do this work, especially when you have a long reaction. In this case, we have only 3 components, but sometimes reactions have many more reactants and or products. So it would take long to calculate everything. And sometimes all we need to know is how much of one substance we have, or did participate in the reaction, or was produced, and we can find that amount only based on one of the reactants, because we know that everything comes in ratios. So I don't need to calculate for every substance as long as I pay attention to one versus another one. So in other words, I only use 2. I know that because the ratios are always following the original reaction, I can figure out what the mass of one substance is relative to the mass of another in this whole process. Let me show you how that works. So here's the theory first of all. By comparing the mass of one substance, so the mass of the sample, the actual mass participating in the reaction, as a ratio to its coefficient and its molar mass, well, I can equate that to the mass of a second substance relative to its own coefficient and its own molar mass. Okay, so I can only work with 2 substances. I don't have to work with everything in the reaction. So don't forget, just as an aside, small m, so the mass of the sample versus its molar mass, that ratio gives me its number of moles. So in other words, I could say this here could be replaced by the number of moles of substance B. It's equivalent, okay? That might be useful down the road. All right, so if I take my original equation and I say, if I have 72.08 grams of H2O, so this substance here that was produced, how much hydrogen did actually react in this reaction? Obviously, hydrogen reacted with oxygen, but I don't need to pay attention to this because, as I just explained to you, because these substances react, appear and disappear in specific ratios, their masses appear and disappear in specific ratios as well. So I don't need to work with all the substances. I can only work with two, and the ratios will always work out. They will always be true. So how do I work this out? I'm going to use this equation over here. So I need the mass of H2. That's what I'm looking for. What is the mass of H2 that reacted? Now this is based on the fact that 2 moles of H2 react, and the molar mass of H2, well, I have 2 atoms of hydrogen, and each atom of hydrogen has a mass of 1.01 grams per mole. Okay, so that's found in the periodic table. So 2 atoms of hydrogen, and there's 2 moles of hydrogen reacting, of H2 gas reacting. What mass of H2 participated in my reaction, considering that I collected on the other side, at the end of the reaction, I collected 72.08 grams. There's 2 moles of water that was produced, and the molar mass of water is 18.02 grams per mole. Again, I found this using the periodic table. So this gives me a mass of 8.08 grams if I do the calculation. So this number over here is 8.08 grams. Now if I do the significant figures, okay, I have 4 digits over here, 3 digits over here, 4 digits over here. So because the mass of the hydrogen in the periodic table, the mass of hydrogen has 3 significant figures, my answer will have 3 significant figures. Okay, now these coefficients, the number of moles that are reacting, these are not measurements. They don't count in my analysis. The only thing that counts in the analysis for significant figures are actual measurements. So numbers that you find in the periodic table are measurements. The masses, or the mass in this case that was found in the original problem, is obviously a measurement. So those are the numbers that you need to pay attention to. And that's why when you use a mass in the periodic table, try to keep at least a couple of decimals, because otherwise you're limiting yourself in terms of the length of your final answer if you round everything. Okay? So, final answer, 8.08 grams of H2 reacted with a certain amount of O2. We're not required to calculate how much. We're not interested in that. But we want to know how much H2 reacted in order to create 72.08 grams of water. And to solve, in case I kind of skipped that step, in case you were wondering how you solve, you have to cross multiply. This times this divided by this will give me my final answer, which is the mass of H2. Okay, so that's how it works. Now let's take a look at a second example. So I just want to show you that it can work with any 2 substances in a given reaction. So in this case, we have 0.36 grams of H2. So we are comparing H2 and H2O. So they're asking if this amount of H2 reacted, what mass of O2 had to react with it. So I have 0.36 grams of H2. I have 2 moles of H2 that react, and the molar mass of H2 is 2.02 grams per mole. If this much reacted, how much O2 had to react along with it to produce a certain amount of water? Well, there's 1 mole of O2 that reacted, and the molar mass of O2 is 32.00 gram per mole. Okay, so if I cross multiply this times this divided by this will give me the mass of O2, and the mass of O2 is 2.9 grams. Again, two significant figures. Why? Because this is my smallest or shortest number. It's 0.36 grams with two significant figures. So my final answer should have two significant figures. In reality, the mass, if you do the calculation, the mass is 2.85 grams. But because we need two sig figs, we need to round this and keep only two sig figs. So because of the 5, this turns into a 9. Okay, so that's for the second example. I have one more, which is a little different. And here we go. So Marco measured the mass of 2 of the substances involved in this reaction. Unfortunately, he forgot to write down which 2. Based on his data, Massimo helps him determine which 2 substances were involved. Below is Marco's data. Which 2 substances do you think Massimo identified? So we know, first of all, that the mass of substance A over its molar mass, actually over its coefficient, times its molar mass should be equal to the mass of substance B over its coefficient times the molar mass of B. So what do I do with this? How do I go about this? Well, let me use the information that is written over here and put it wherever it belongs inside my equation. So I have the mass of substance A, which is 10.0 grams. And I have the mass of substance B, which is 39.88 grams. Now, I don't know what the coefficients and molar masses are for A and B. Actually, I do have the molar mass for substance A, but I don't have its coefficient. So let me do times, or actually let me put a bracket. I know that the molar mass for this substance is 16.05 grams per mole. But since I don't know what substance it is yet, I don't know what to put as a coefficient, but I'll get back to that. And I have the coefficient for substance B, which is 2. But I don't know what the molar mass for B is. Okay, so it could be either this substance or this substance. I don't know. But what I know is the molar mass of A. So by process of elimination, I can figure out which of these substances should have a molar mass of 16.05 and therefore determine which coefficient goes in front. So H2O has roughly a molar mass of 18. That doesn't work. CO2 has roughly a molar mass of 44. O2 has a molar mass of 32. And CH4 has roughly a molar mass of 16. C is 12 and H is 1, or 1.01 I should say, and C is 12.01. So it does add up to 16.05. So I now know that this has to correspond to CH4. CH4 has a coefficient of 1. So that means there's a 1 that goes here. And I have identified substance A. Substance A, because of its molar mass, has to be CH4. Now I need to identify substance B. How am I going to do this? Well, I'm going to find its molar mass. That's now the only variable in this whole equation that is missing. And by finding the molar mass, I will find the identity of substance B because it is a specific characteristic. So if I solve, what do I get? I get that the molar mass of B, and again I have to cross multiply, I get that the molar mass of B is 32 grams per mole. And which substance between O2, CO2, and H2O has 32 grams per mole as a molar mass? Well, it is oxygen. It's O2. And so I'm able to identify what is substance A and what is substance B. So that's how you would go about this. So that's it for this lesson. Hopefully it clarified things. If you have questions or if you have problems that you have trouble with, Ask your questions in the comment section below. You can always send me a quick message as well, and send me maybe a picture of your problem, and I will give you a hand with that. And if it's a typical problem, maybe I could use it to make a subsequent lesson with just problem solving if you send me good typical problems. In the meantime, take care of yourselves, and I will see you around for your next lesson. Bye!